I'm Radu. This is my colleague Rafał. We work at Sematext. We do things like consulting, training, and production support for Solr and Elasticsearch. We're here to talk about Lucene similarities. Before we dive into it, let's just deal with some administrative stuff. There's been a confusion. Anyway, regarding the schedule, and in the printout you can see that there are two talks, one after another. This one and one about, I'm not sure if I can, okay, and one about time-based, time series data.
Basically, there were two talks in the printouts, and we'll be delivering one about the similarities for 40 minutes. And if you want to talk about the time-based data, come join us at the booth. So we'll be happy to do that. But for now, for the next 40 minutes, we'll talk about similarities.
Right.
Doesn't work?
Right. I'll just talk louder. That's fine. So again, some things before we start. We're going to do some demos. Does this work? Yeah.
Yes.
Okay. So we're going to do some. Like this? Ah. So this doesn't work. This works. Oh, thank you. Okay, cool. Aha. All right. So we're going to do some demos, and you can see the code on GitHub. If you want to follow, you can not necessarily like follow as in do the same demos right now, but like if you want to do this at home, there's everything there, including some data that is open, so you can kind of play around with this, make your own variations. We're also going to talk a bit about the the theory behind each of the similarities. We're not going to be comprehensive about it though, but you can find a lot more information about like the math and the intuition behind that on our blog, and the link is there. Right. So we're gonna just go through all the similarities that come out of the box with Lucene. We're also gonna show you how to build a custom similarity, and then we're gonna put everything together. So like, how do you combine the score if you have like one similarity in one field and another similarity in a different field? So first one that we want to mention is the classic similarity, the one that used to be default until Lucene 6 changed it to BM25. So this is TF-IDF. Who here knows about TF-IDF? Right, so almost everyone. So for those who don't know, this is basically three important components of the score, which we'll find over and over again in other similarities. So first one is the term frequency, meaning if I search for cat, a document that has multiple cats is going to be more relevant than one that has fewer. Then there's inverse document frequency, meaning if I search for, let's say, cat and dog, and let's say in my data set, dog is a rare word, then it's going to have more weight than cat, which can be a frequent word in our data set. Okay? And then there's document length normalization. So if I have a longer document, just by sheer randomness, it's going to be more likely to contain that term. So we're going to adjust the score for that. All right. The new default is BM25, like since Lucene 6. And the big difference between it and TF-IDF is the way the term frequency works. So it grows closer to a ceiling that you can configure with this K1 parameter, right? So the default is 1.2. If we adjust it, then we will allow scores to grow higher, or just make them closer to each other. And we can also adjust how much we care about length with this B parameter. So if we increase the B, we care more about document length. If we lower it, not so much. So let's jump into a demo and see how that works.
Let me help you with that.
This is going to be interesting. Okay. Does that work? Okay. So I have a default similarity. I can't see the screen, dude. All right, so I have a default similarity. It's like playing the piano. And I'm going to run a query. So this is just out of the box. let's say I search, so this data set, which is, as I mentioned, open, this data set is mostly about clothing, right? And of clothing, most of those items are shoes. So let's say I search in the description field, just to look into one aspect of the query. I'm searching in the description field for both wool and durable, okay? And what I get is, you don't have to squint to read everything here. Basically, I have two things that I would potentially want to fix. One is shorter documents tend to rank higher because of we penalize by length. And then the other one is, if I actually scroll all the way to the bottom, the last document, you have to trust me on this, it's not necessarily less about wool and less about durable than the first document, and yet it has less than half the score. So what I want to do in this case is I want to bring the scores closer to each other, because if you think about it like in a production sort of setup, I don't want two documents with the same type of relevancy to have that big of a gap in the score, because it's going to just break everything. And the way to test this, I mean, obviously here in the demos, we'll just show you like one example. Normally you would have a bunch of tests that you would use to figure out whether making a change in the similarity actually makes a difference for the better or for worse. But here I'm just going to make this one test. So to fix the problems I've been mentioning, I'm going to tweak the K1 and the B parameters that I've been mentioning. So you'll do that in the schema. In the field type, you have a similarity block where you specify the similarity factory. Like in this case, it's BM25 similarity factory. And what I'm going to do is I'm going to lower both K1 and B. So lowering K1 means I'm going to lower the ceiling, which means our scores are going to be closer to each other. And then lowering B, I'm going to lower the importance of document length. Okay, so let's upload that and see how it goes. So it's basically all about uploading the configuration and then reloading the collection. I don't have to reindex or anything like that. Now, if I rerun the query, first of all, the order is completely different. Now I have a mix of longer and shorter documents in the beginning. The top documents have like 5.6 score, and the lower ones have like 3.6. So now I don't have like the top document is only like 1.5 times the score of the bottom document, is not 2 times as it is. So now we have scores closer, and document length isn't that much of a problem. So just to summarize, this is what you can tune. You can tune the weight of like frequency and also document length, and it's usually a good default, which is why it's default.
Okay, so the next thing that we would like to talk about today is divergence from randomness. Compared to BM25 or TF-IDF, it's a different approach. It's more of a framework that you can think of, and you can think of it as a random distribution of how the term actually appears inside the document. And we have a distribution, the basic models. There are 4 of them right now in Lucene 8 when it comes to that similarity factory, G, I, E, E, N, E, and so on. You can see that. That they actually define the distribution. And the higher score will be given to those documents that have the term from the query more diverge from the original model that we have chosen. You can think of it, of the basic model, more or less as the IDF, more or less. And there is also something called after effect that affects how the score is actually calculated. We have 2 possibilities here, Laplace and Bernoulli. Laplace is basically a 1.0 in the implementation in Lucene. So we'll see how that goes. And then we have something that's called normalization factor. Basically, we take the term frequency, so how often the term appears in the document, and we normalize it so we can have better score control, basically. And there are 5 normalization factors here. One that is called non, which takes the basic term frequency, and H1, H2, H3, and Z. So let's look actually at the normalization factors and how they affect the score when using the DFR similarity. So first of all, we have the H1. The idea is that the first three ones that I will be talking about is that we take the term frequency, multiply it by a certain parameter, it's called C in the similarity, and then we multiply it by the average field length divided by the document field length. And how does that affect our scoring capabilities? Look here. You have the bottom line that shows us the model without any kind of normalization. And then the more you go with the C, the steeper the curve of the score calculation is, which means that the documents with the higher term frequency, so the documents that have more terms or less or more terms from the query, will be put on top of the document list, right? So higher, they will be given a higher score. This is the first normalization factor. Then we have the H2, which is very similar to H1, but it is less steep when it comes to the score curve itself because it uses a logarithmic function. So we can see here as well that the steepness of the curve is slightly lower compared to H1. And again, we control it with C with the same principles. The higher the C, the more term frequency matters for our score calculation. So if we want larger documents to be on top of our results, then we push the C up higher. The last one that is actually based on the average field length divided by the document field length is called Z. The Z parameter here is an exponential, controls the exponential function, and it's between 0 to 0.5. And again, we multiply the term frequency with it. But here the difference is not so, you can't see that much of a difference, right? Because you can see those scores are really comparable or close to being comparable to each other, even with changing the Z from 0.1 to 0.4. The last thing that when it comes to normalization factors is the H3, which has similar name, but the idea is a bit different. We have the mu parameter, and instead of taking the average field length here, we take the total term frequency from a shard or collection, depending on how your architecture looks like, number of fields in token fields, and then divided by the document field length. Again, adding the mu and then multiplying it by it. So how does that work in a situation, sorry, not yet. So you can see this time, this is a bit different. The one without normalization is still the one closer to the logarithmic function, but the ones with H3 normalization look more or less linear. It's not a linear function, but closer to it compared to the others. So again, something, if we want like a more linear score growth, this is something to go for. And of course, as we promised, some kind of a demo to show you how that all actually works. So first of all, I would like to tell you about some kind of use case that we can choose here. So I'll be using a DFR similarity, as you can see here, and with the basic model G, with an after effect L, so 1O, nothing with the after effect, normalization factor H2, and some default C. How do we came up with? It's more or less an experiment, right? We try to choose the first some defaults and then experiment with that to get to the results that we would like to have. Okay, so let me actually upload that. Oh, here it is. And let me show you the results. Oh, come on. We'll be searching for comfortable women's shoes. The categories field is very short. So let me show that. This is very short. The categories field, it has 2-3 term stops in this data set, but the reviews are quite are larger. And the idea here is that we would like to get to a point where the documents with large reviews, the beefy ones, the ones that have a lot of terms, are on top. We can assume the use case where we think that when the customer actually writes a review, it may be a better document. Maybe those shoes are actually better because someone took the time to write the review like a better one, and so on. So what we can do? With the default, of course, we have some of the reviews. They are not quite small, but still they are not large. And believe me, they are reviews for a few pages of text. So we'll try to put them on top of the results. So first of all, what we can do, we can change the after effect and see how that affects our score calculation. So we change the L to Bernoulli, and again, we'll upload the data, the actual configuration, reload, and let's check how that affected the whole result set. You can see that the top results changed. They are short. Something's not right yet. But if we go down, we can see that some of the documents that are larger, like here, are already pushed high. But remember about normalization factor. We said that the C, if we go up with the C, we can push those documents that are large even further up. Let's try that. Why not? So we have C set to 7.
Make it 50. Make it 50.
As you
Make
wish.
it 50.
So
Go
50.
wild. This is extreme, but still.
Yeah. So let's upload that and let's see what happens. Okay. Now that I reload, look, Firefox even didn't open that data by default, but look at the documents here. Those are like enormous when it comes to the number of terms inside the reviews field. So we got actually from a point where those short documents were on top to a point only by modifying the similarity where the documents that are large are on the top themselves. And this is how you can actually experiment. But remember, DFR is a framework. It's not easy to use. It's actually quite complicated. You control more or less the IDF and the .lang combined by using different models, different after effects, and normalization factors. And normalization factors will come back.
They will. All right, let's go with divergence from independence. This is a much simpler similarity. I just got lucky. So this revolves around the concept of an expected frequency. How many times do we, this is a probabilistic model, right? Like how many times do we expect just by sheer randomness for a specific term to appear in a document? How do we calculate that? Well, let's say I'm searching for cat, right? I'm taking the total number of occurrences of cat in my index, and I divide that by the total number of terms in my index. And that's the probability of any term to be a cat. Okay, if I multiply that by the document length, then I just get the probability of cat to occur in my document, assuming that cat and my document are like two independent things. That's the assumption of independence, right? So what we will do to generate a score is we will take the actual number of cats in my document and we're gonna subtract what we expect. And the further away we diverge, the higher the score. And we have 3 tests to choose from. Here we will show only one of them, the standardized one. So basically take the actual frequency, we subtract the expected frequency, and then we divide by the square root of the expected frequency. And the 3 lines you can see there are like to show how score grows depending on how rare the term is. So the green line is a more frequent term that's going to just grow slower than a rare term, which is going to just go high with yeah, that's the technical term. So let's try that out. But before we do that, this is a pretty important mention. For this similarity, don't remove stop words, because if you remove stop words, you basically screw up the length of documents kind of arbitrarily. And length is very important in figuring out what the probability is. And also, as you probably all know, stop words are not always real stop words.
Give me the microphone.
Yeah, I'll show you that in a bit. Right, so let me put the default configuration back to show you a different problem. So this time I'm going to search, let's say, for comfortable shoes. So shoes goes into categories and comfortable goes to reviews. Now the problem that I have here is in the 7th position, it's actually the 8th because we count from 0, we have a jacket. Why it's that? It's obviously a very comfortable jacket, and it does match shoes because in the categories I have shoes here among other things. So shoes is a terribly common word. And I took some sandals that are in the 71st result, and let me just show you how the debug output of them both looks like. So this is the jacket, right? It is very comfortable. It has 0.94. The sandals rank much lower. It has 0.87 for comfortable. But the weight of shoes, because it's such a common word, is like next to nothing. If you see, like it's 0e, it's to the power of -6. So it's like nothing. Even if it's twice as high as the one in the jacket, it's still like next to nothing, okay? And this is one of the situations where DFI can help, because DFI doesn't really care about what the distribution of that term is. So it's the same thing with as before. You change the similarity here. We specify DFI similarity factory. I have to specify which test I want to do out of the 3. Standardize is what I would go for. How do I know that? Just testing. And okay, so let me upload that. Right, and let's rerun the query. Okay, now if I look for the sandals, first of all, they bubbled up. Let's look for this ID. Right, now they're on the 6th position, the sandals, up from the 71st. And if we, and the jacket is, I think, is nowhere to be found. Let's actually look for the jacket. Yeah, it's not even in the top 200. Trust me.
Come on.
Yeah, it's bad. It's really bad for the jacket now. Why is that? Well, now the sandals actually have a significant score for shoes, because it appears 2 times, and we expect it to appear like 1.16 times. Meanwhile, the jacket has exactly 0, because the actual frequency is smaller than the expected frequency. And Lucene doesn't allow negative scores. I mean, the original paper, you would actually generate a negative score. Lucene doesn't allow that, but at least we set it to 0. So it's not a shoe, which is precisely what it is. So to summarize, DFI is advertised to work well on a diverse sort of data set, like when you don't know what the distribution is. And there's nothing to tune, really. You just have three tests to choose from. If they work, good. If they don't, tough luck.
When it comes to tuning, let's get back to DFR. I'm joking, but information-based similarity is very similar to DFR that we talked about. Actually, in Lucene code, there is a comment that says that eventually they both can get merged together. Maybe that will happen, but for now, this similarity actually asks a question. How much information we get from a given term inside our data? So similar to the DFR similarity, again, we have multiple factors that we should consider whenever dealing with that similarity. We have a distribution, which is more similar to what we call the basic model in the DFR. We have log logistics and smoothed power law. Actually, the smoothed power law will be slightly less steep when it comes to score calculation because it uses a logarithmic function. Then we have a lambda, or as we call it, retrieval function that controls how the distribution works. And we said that we'll get back to those normalizations, and we are actually back because information-based similarity uses the same normalization as DFR, so H1, H2, H3, Z, and none. Let's look at one of those distributions. For example, the log logistics is very simple. It just takes a logarithmic function of normalized term frequency and divides it by a lambda. And the lambda is that retrieval function that we talked about, right? So if we would consider a lambda a static value right now, we can see how the log logistic distribution will actually work when it comes to when it comes to score calculation. you can see the 0.1 red is on top, and the higher the lambda is, the score is actually variating because 0.8 is down, like less steep curve, and the score will be eventually lower. So that's how it works. And those retrieval function also tells us the average of the document information by each query term. So it takes the term and answers the question, okay, how much information about the document that was found is actually brought by that term for the score. And we have two of those. First is the DFs. Basically, it takes the document frequency and divides it by the number of documents inside our shard or collection. And it basically the number of documents matching, right? And the second is about total term frequency. It takes the total term frequency, not the term frequency itself, but the total appearing inside the shard, and divides it by the number of documents. Enough theory, a simple demo that will show us exactly the opposite what we did with DFR. Let's now assume that some of those reviews are nasty, and we don't want actually to show that to customers, right? Let's put those shoes that have nice small reviews on top, and the ones that are large, well, let's put it down. So to do that, I'll first, of course, show you the IB similarity. So we have the IB similarity here. It uses a distribution of smoothed power law with the DF lambda and no normalization here. That's the key point for now. And if I'll upload that, you'll see how we'll be still looking for actually comfortable women's shoes, just for reference. So hopefully nothing will blow up. Should be working. And now let me run the query here. So our defaults that we have chosen are actually more or less pushing the large documents on top. You can see this is exactly the same thing that we did with DFR. We have lots of those documents on top. So we can try lowering these and choosing the different lambda or different distribution. In the demo, I think we wanted a different distribution here. So let me go to LL and upload that once again to show you how that works. You have to actually believe me here that at the end of the results, some of the documents that were shorter were pushed a bit higher, but still on top of the results, we still have those nasty large documents that are here. So, and of course, score changed, but that doesn't really matter for us because we still are not at that point. And that's where the normalization factor comes in again, because we are this framework that we can actually use that. So let's try again with H2, and let's try with that C that Radu suggested to put like 250. Let's now not go that way. Just for a reference, remember that when we pushed up very high, then we got those documents on top. So now we need to do the opposite. We need to normalize that term frequency to go down. So let's see, for example, something like 5 or even less. 5, just to show you that those results will not be perfect. But once we push that and refresh the data, you can see that some of the documents look very nice. On top, they are short, but it's not that perfect. And this is the large documents. Of course, we could go further on, but we don't have time. But this is the beginning, right? The proof of concept that we can do that with IB similarity, and we should just choose like a different distribution, a different retrieval function, and play with the normalizations. Maybe H2 is not the best. Maybe H3 would be better here. Something for a homework. So getting back to that, remember that this is a framework like the DFR, and it's newer, and in the paper in general, it's said to be better choice than the DFR itself.
I think some people just came in for the time-based data talk. There's been, let's call that a typo in the printout. The whole slot is for similarities. So you're welcome to stay here for similarities and maybe talk later about time-based data.
But if you need time-based data, come to the booth after the talk. We're happy to talk about that.
All right. So that being said, let's move on to language models. Language models are very similar to DFI in the sense that they're probabilistic models. What's the probability of a term to be our term, right? Same thing here. How many cats we have, and we divide that by how many terms we have in the whole index. That's our probability. That's the language model of our index, right? And there are two language models to choose from. Here we're going to focus on the Jelinek-Mercer one, which basically divides the language model of our document by that language model of our index. Okay, so the language model of the document is term frequency divided by document length, right? That's the probability within the document, okay? And then we have the index-wide probability. And we have this lambda, which we can choose, which we can tune. That's the difference between this and DFI, because we can use lambda to tune what the weight is of each, okay? So let me show you how that will work.
I'm here.
I'm going to take a completely different query now. One that's, I think, more realistic for the use case. Take a very long query, run that against a catch-all field, and see how that works. What?
You need BM25.
Yeah, let me go back to the default. Because, oops, error, demo. Okay. So I'm going to run this against the default underscore text field that Solr has by default. You can just enable it. So I'm going to search for women, side zip, high heel, leather, ankle boots. Okay? I'm not going to search with and because usually that's a bad practice for a long query because chances are that not all the interesting documents are going to have everything. But I have a problem here very soon. So this is a man's shoe. I'm searching for women's shoes. This, by the way, it's not what you think. It's a fake leather, right? No.
Okay, let's blame it on Firefox.
This is much nicer, I think. Yeah. Anyhow, so this completely took over. Okay, so the men's shoe it's up on top. We don't want that. And why? Well, it's the same kind of thing as with DFI in the sense that if we look at the debug output and we compare this debug output with the debug output of an actual shoe that meets all the terms that we were searching for, what you can see is the weight of women, which is very, it's a very common word in our data set. That weight isn't, changing the score a lot. And if you look closer, you will also see that the scores for what are accidentally, in this case, low frequency words like side and zip, this weight is high. So the men's shoe, ranks high here, while the women's shoe has more weight for things like heels or leather, which are high frequency terms, so they don't get enough weight, right? So we're going to use the language model like the Jelinek-Mercer here, which is advertised to work well for long queries, for much of the same reasons as DFI. So let's do that. I'm just going to upload it. Actually, no, let me show you how this looks. I'm going to choose a lambda of 0.4. I want a relatively low lambda so that I give the document model more weight, right? Like if you have higher frequencies, you should get a higher score. So let me upload that and rerun the query. Right, so now if I search for men, you can see this is on the 11th place, okay? And the other one is even a bit higher up at the 7th place. And the reason for that is now I'm going to have more weight for things like, for more frequent terms, right? Women being one of them. And this kind of brings a balance. It's not a huge difference, not like with DFI. Like the total score of this is 17, the total score of this is 16. So it's not as aggressive as DFI was, but it's still enough to fix this particular problem, right? So in short, LM is like DFI, but you can configure it.
And
oh,
we
that was an
really,
overgeneralization. Anyway.
yeah, watch out. And we really left the nice stuff at the end for those of you who are still with us. So what if any of that doesn't work for us? Can we do something? And yes, we do. Solr allows us to create a custom similarity and plug it in. We need to do some Java code. We need to get ourselves dirty a bit, but that's really easy. So first of all, we need to create a similarity factory. It's pretty easy. This is the part that will be used in our schema. So we extend the similarity factory class, and we need to have two methods, basically. The first is the init that allows us to read the properties from the schema. So anything like those C that we've seen, the lambdas and so on, it can be read here. And it's run during initialization of Solr. And then we have the get similarity, which returns our instance of similarity. We create it if it's not there, and then return it otherwise. So that's simple. So next, we need to create that activate similarity that we have on the screen. So again, it's a very simple code. We extend the similarity class, and we have two methods to implement. Compute norm, in our case, it's one, as simple as it can get. We have the invert state here, so we can get some information for the norm computation if we need, but for now, we don't. And we need the sim scorer to be returned as well in the score method. Basically, some kind of scoring algorithm here. We have a boost here, collection statistics, and term statistics to use. But we won't use that. We'll just create an activized sim scorer, which, as I promised, is very simple. In our case, with that simple similarity that we have here, we will only care about the frequency of the term, and we will assign a score equal to the frequency. So if something appears 10 times in a document, the document score should be 10.
Should.
Can I? OK. He insisted. So first of all, the schema, it's very simple. We just take the com Sematext activate similarity factory here. We already have the jar deployed in a way that Solr knows. Like we introduced the lib directive in the Solr config, and we have Solr already knowing about this extension. And let's now look at how that actually works. So again, we'll start with uploading the configuration to Zookeeper and reloading the collection. And two simple queries right now. Let's forget about comfortable women's shoes. Let's just care about the shoes. So quickly as I can get, you can see that I have a single document. It doesn't really matter much. The score of the document is 7. And this is because the shoes in the term frequency of the shoes right now is 7, as shown in the debug output, right? So the score. And finally, let me just show you one last thing before Radu comes in. I know he wants to show something as well. So just a second. For both terms, if we have both terms in a query or more, it will just sum the score in general. So as you can see here, one term's score is 3 and the other is 21, and the whole score of the document is 24.
All right. So last bit. No, I'm okay.
No?
So last bit, I want to show you like how you, custom. It's for custom stuff. So the last bit, like how do you combine similarities? And here I just want to jump into the demo and show you a few debug outputs. So, which is not really a demo, but you get the point. So here, if I run a query that looks like this, durable shoes that are also comfortable, right? And with BM25, and I've been using the BM25 that we've customized before with like 0.4 and 0.7, we can see the problem, the same sort of problem that we've seen with other similarities, that frequent words such as shoes get a very, very low weight. Okay, so let's say, okay, we're going to use DFI to fix that. And now we're going to get, if I'm going to use DFI for categories and for reviews, but leave BM25 for descriptions, which looked fine to me, now I'm going to get a very high score here for the reviews field. That's because DFI generates a wider range of scores, and if I combine them, which Lucene will do by default, like in the Boolean query, is just going to add those scores up. The problem is that the reviews will dominate our score. Now, how can we fix that? One option is obviously to use boosts, but the other option is you can use a custom similarity, and you can just copy paste the code from, like in this case, DFI. If I take the code from Rafał and for the simple similarity.java class, I just copy paste the code from DFI, and then I can just change the score here. This was the original one, right? Like I take a logarithm of base 2 out of the measure that's given from our test. So here we just use a base 7 logarithm, or we can just logarithm everything, or we can just alter the score in a way that produces a narrower range of scores, but yet it's still like the function is still kind of growing, so we have the same order. So with this particular thing, if we just apply it, you will see that the debug output, like now I have much more even scores, so you can combine different similarities on different fields, depending on what works best.
41.
Yeah. So that's pretty much all we have. Visit us at our booth. We do Solr monitoring and more. Thank you very much, and we'll be here for questions. Unfortunately, we don't have that much time.
Thank you.